A good day to Dr. Liew Cheng. Today we will be presenting on the topic of closed system reversible process and enthalpy. We begin with the historical background, which tracks the development of thermodynamics from early theories to the formalization of enthalpy. The concept of heat and work is considered two subjects before 1850. Sadi Carnot and Clapeyron pioneered the study of steam engine efficiency. In 1824, Carnot introduced the Carnot cycle, showing how heat converts to work. Later, Thomson built on Clapeyron's work, which focuses on heat conservation. In 1850, Clausius formalized this as the first law of thermodynamics, establishing energy conservation, and later introduced the second law, which deals with entropy. The concept of enthalpy started taking shape in 1875. In 1909, Keith Landler expanded on Gibbs's ideas, and a physicist coined the term enthalpy. By 1922, A.W. Porter formally defined H as enthalpy. Finally, Emile and Clausius connected enthalpy to the Clausius-Clapeyron relation, solidifying its place in thermodynamics. Enthalpy in a closed system reversible process can be determined by calculating the enthalpy change for forward reaction and backward reaction of a process. In a forward reaction, energy must be supplied to system because energy is required to break the bond between atoms. After that, energy will be released because bond already formed between products. The net change in energy over this reaction is called the change of enthalpy. In backward reaction, the change of enthalpy will have the same value with forward reaction, but with opposite sign. This slide provides important definitions. A process is reversible when its direction can be reversed at any point by an infinitesimal change in external conditions. Secondly, if a boundary of a system does not permit the transfer of matter between the system and its surroundings, the system is said to be closed, and its mass is necessarily constant. Enthalpy is the sum of the system's internal energy and the product of pressure and volume. The energy balance for a closed system with a homogeneous fluid in a reversible process relates the change in internal energy dU to heat transfer, dQ, and work dW. For a reversible closed system process, dU equals dQ minus PdV, where dW equals negative PdV. At constant volume, the change in internal energy equals the heat added to the system. To simplify, enthalpy H is defined as H equals U plus PV. Since U, P, and V are state functions, H is also a state function, allowing for calculations of finite state changes. Here we present a 3D model to help visualize the thermodynamic process in a closed system. This model demonstrates the volume expansion and energy transformations during the reversible process. Imagine this gas contained within a piston cylinder setup. Initially, the gas is confined to a smaller volume, exerting pressure against the piston. The expansion occurs by applying a small force on the piston. As the piston moves outward, gas molecules spread out to occupy the larger volume. For an isothermal expansion of 1 mole of ideal gas at 273 Kelvin, the gas expands reversibly from 22.4 liters at 1.00 atmospheres to 44.8 liters at 0.5 atmospheres. This problem is solved using MATLAB. Since the process is isothermal, the change in internal energy delta U and enthalpy delta H are both zero. The work done by the gas, W, is minus 1.57 kilojoules, and the heat absorbed, Q, is plus 1.57 kilojoules. These results reflect the balanced energy exchange in an isothermal expansion, where the heat absorbed by the gas equals the work done by the gas on the piston. This slide shows the manual calculation for the previous question. This slide includes the references that we used for finding the information related to reversible process, closed system, and enthalpy. That concludes our presentation on closed system reversible processes and enthalpy. Thank you for your attention.